So we're now going to review a couple of different definitions we've learned before when we were dealing with light, but just apply them to waves in general. So the first one is going to be reflection. So the very first thing we did in light optics was light reflection. And it is very much the same thing. It's that when a wave bounces off a surface. Now, you may be asked of an example of wave reflection. The most common one is an echo. So if you've never heard of an echo, it is essentially when, if you imagine yourself standing inside of a cave, for example, or really anything natural, if you say anything, then the sound waves will travel. Actually, let me get my laser pointer. So if we're standing here, the sound waves will travel and then bounce back. So this happens a lot in natural objects because a lot of synthetic materials, or actually a lot of building materials, are designed to reduce the amount of echo, which is why a lot of times when you do echo, it is inside of caves or somewhere similar. The next one we're going to do is refraction. So the one we did after reflection was refraction, and it's basically the same thing. So when a wave changes speed as it changes medium. This is also something you might cover in geography. So you will actually cover wave refraction when you get to coastal processes. You'll learn wave refraction in slightly more detail when it comes to the sea. But also, because the water in this case has a higher refractive index, again, we're chucking terminology back and forth between chapters, but because this has a higher refractive index, it will actually take longer for you to say something underwater as opposed to above it. So I think we briefly discussed this in refraction, or at least to some extent. That's because the internal molecules will actually vibrate slightly slower than the molecules inside of air due to the properties of the refractive index. So next up we have diffraction. So diffraction actually occurs when a wave passes through an opening, and it is similar to that of the wavelength of the wave. We can see here that as soon as the waves, they travel in straight, but when they hit a gap, they start to spread out. And when the gap is roughly the same as the wavelength, then we refer to that as a large aperture. So this large aperture doesn't mean it's spreading out a lot. It's basically going along the same path with like some slight deviance. But when it's really small, we call it a small aperture. So we can see here that it's really small compared to sort of the distances between each of the crests, and therefore it spreads out a lot more due to that change in aperture. So we can see that because if we actually shout out of a window, for example, the sound might diffract and sort of spread out. That's because a sound wave is large enough that it can actually diffract through a window. However, light does not, because a light wave is roughly on the order of a couple hundred nanometers. A nanometer, just as a bit of a refresher, if you don't remember the scaling factor for nanometer, nano means 10 to the minus 9. So a lot of these will actually be on the order of between 4 and 7 by 10 to the negative 7 meters, or 400 and 700 nanometers. So yeah, as I said, we've actually discovered that sound have wavelengths on the order of about a meter. We saw when we actually solved for middle C that it was about 1.3 meters. So it is entirely possible that sound can actually diffract for a window pane, whereas light cannot. The next one is going to be wave polarization. Now we're going to bring our old friend, the two-dimensional plane back, but it is essentially restricting light to vibrate only in one plane. So we can see here there's a little bit on polarized sunglasses, because they're the most common usage of polarization. And this isn't taught properly in a lot of physics classes. However, the reason why polarization actually occurs is because there's a special polarizing filter, and inside of it there's a bunch of molecules. So again, back to all from the molecules and vibrations. So when light comes in, either unpolarized or polarized, it really doesn't matter in this case. But let's say it comes in unpolarized, so it vibrates in all these random directions. Then when it comes in, relative to a thing known as the polarization axis, so we'll say the polarization axis is there, so the PA, polarization axis. then only the light that is parallel to the polarization axis actually passes through. So in fact, it'll be that light there as it passes through this polarizer. The rest of the light actually loses its energy into vibrating these internal molecules. Again, a lot of things with vibrating molecules here, but that's essentially how it works, is that all this light gets input here as energy to move these little things around, except for the ones that are parallel to the polarization axis. Now, a key thing is that longitudinal waves cannot be polarized. So we can polarize all transverse waves, which includes a lot of light rays. So light rays are actually the more common one, as you can see here. So light rays can be polarized, whereas longitudinal waves cannot. And the final thing we're going to be discussing is interference. Now, again, I've keep forgetting to rub out the annotations I provided the first time, and that's really poorly drawn. So interference occurs when two coplanar waves collide, and they will create one superimposed wave. So superimposition is just combining the two waves to create one. That's all that is. Now, we can get what is known as constructive or destructive interference. Now, constructive interference is when the sum of the amplitudes gets bigger, and we can get what's known as total constructive interference when they're actually in phase with each other. So that means they have the same phase shift. So when we're comparing them as I did here, or that's actually destructive, but essentially if we compare two general wave equations, or in terms of simple harmonic stuff, then they will get total constructive interference when the value of epsilon is the same. So if you just want to remind yourself, the displacement of an object undergoing simple harmonic motion is a sine of omega t plus epsilon, where epsilon is the phase shift. So actually constructive interference is used in guitar strings, which we'll get onto on the thing known as stationary waves. And then destructive interference is when they're phased out by a factor of pi. So in fact, the value of epsilon, or the relative value of epsilon between them, so one of them is actually pi radians bigger. So as you can see here, one might be a sine omega t, and the other might be a sine omega t plus pi. And what that will mean is that they will essentially cancel each other out perfectly. Now, this doesn't happen all the time. You might get like a very small amplitude when doing destructive interference, but that's essentially what total destructive interference is, when the two waves are out of phase by pi radians and essentially create a flat line with no amplitude whatsoever.